know that the abstract algebra or modern algebra, in abstract algebra and modern algebra, we are studying about different types of what algebraic structures, and those algebraic structures, we are some of us are familiar about those algebraic structures. They are groups, rings, fields, modules, vector spaces, lattices, and algebras. We are studying about various algebraic structures like this in abstract algebra. So I will start with very elementary one. I will first of all, we can see before starting an algebraic structure, everyone should know what do you mean by a binary operation. So how many of you have thought a binary operation in the proper definition way? We have to see. If you take any non-empty set S, a binary operation on a non-empty set means what? First of all, we should accept that it is a function. Whatever the notation we are giving for a binary operation on a non-empty set, we should accept that it is a function. It is a function means it should have a domain. It will be it has a domain. It is nothing but S cross S to the same collection S. So how this function will be a binary operation. If we need binary operation means in word itself it is that we need two elements at a time to operate. So we need two elements at a time to operate means we need to take two elements at a time means we have to take an element from the Cartesian product of the given set. Then it should go to where it should be defined as A star B. That element should be there in the given set. So this is the way of defining what a binary operation. So once the binary operation is known with us, then we should know what do you mean by, I told you that these are algebraic structures. These groups, rings, fields, all are algebraic structures. What do you mean by algebraic structure, or another name is algebraic system? Algebraic structure or algebraic system means what? If you have a non-empty set S together with a binary operation defined on it, one or more than one, not only one, if you can take what more than one operations defined on it. So such system, that is it's a non-empty set together with one or more one or more binary operation defined on it, such structures are called what? Algebraic system or algebraic structure. So once you have algebraic system or algebraic structure, right now you have a algebraic structure means you have a non-empty set together with a binary operation on it. Then if that binary operation satisfies the associativity property, you know that also what do you mean by associativity property on a non-empty set? Yes. If A star is the given algebraic system means what should happen? A star B star C should be equal to A star B plus A star C. If it is true for any three combination from the given set, then we can tell that such algebraic system is called the semi-group. Semi-group means what? An algebraic structure in which a binary operation is associative. So now we got a special structure that is nothing but called semi-group. In a semi-group, now the binary operation is just associative. I am going to add one more condition to that one. That is, I am going to add the existence of identity element in this algebraic system. If the existence of identity element is added to this algebraic system, then the new algebraic system is called the monoid. A semi-group in which the identity element exists means what? It is called a monoid. I am just talking about some of the basic concepts here. So from a semi-group, we reach to another structure that is monoid. So based on this binary operation, if you add one more condition to this monoid, that is, now we have associativity property, we have identity property, then I am adding one more property, that is existence of inverse. Existence of inverse with respect to the given binary operation. then such algebraic structures are called what? Group. Every majority of them will be familiar with that concept, that is group. So in group, first of all, it is an algebraic system. In that associative property, existence of identity and existence of inverse. And you have seen plenty of examples for groups as well. And here, if the binary operation is commutative, then we are calling it as an abelian group. So if you observe these structures, semi-group, monoid group, abelian groups, we can give a diagrammatic representation here. So you know that every abelian group is a group, and every group is a monoid, and every monoid is a semi-group. So that means the general structure among all these is semi-groups. So if you know this diagrammatic representation, then you can come to know the interrelationship between what? The groups, abelian groups, monoids, and semi-groups. So now I will come to a different structure, that is nothing but ring. In groups, you have seen that in groups we need only what? An algebraic system means uh, take a non-empty set together with one operation, one binary operation. Whereas here in rings, what we have? In rings, you have to take a non-empty set. We used to call it as, generally we used to call it as R. And I'm taking two operations there. That is, one is addition. Addition, to define addition, it should go from where R cross R to R. Each ordered pair is going to A plus B, and each ordered pair is going to A dot B. And with respect A into B, that is addition and multiplication. With respect to these two operations, we need to uh, satisfy some axioms. What are those axioms? The first one is this non-empty set R together with addition, it should be an abelian group. That you already know what do you mean by abelian group. So first of all, R plus should be an abelian group. We have a second binary operation here. So with respect to that operation, this R dot should be a semi-group. What do you mean by semi-group? That is with associativity property. That is R plus should be an abelian group and R dot should be a semi-group. And the third one is multiplication should be distributive over addition. That means you take any three elements A, B, C in R, A into B plus C is equal to A into B plus A into C, and the other way. So if these conditions are satisfying, that is R plus is an abelian group and R dot is a semi-group, and both the distributivity property holds, then we can tell what the new algebraic structure, that is R together with addition and dot, it is a ring. And you can see here that in R, here with respect to multiplication, it has to satisfy only the semi-group condition. In that one, if the multiplicative identity exists, that multiplicative identity we generally denote it by one suffix R or 1. If that multiplicative identity exists, then that is called the unity of R, and such rings are called rings with unity. Rings with unit. That is what this is the point I have told now. Identity element, and where I have told that such rings are called ring with identity. So here in this is a very simple example for you for a ring. If you take the set of all integers with usual addition of integers and multiplication of integers, you can see that Z, the set of all integers, is a commutative ring. And you know that with respect to multiplication, Z has the identity 1. So it is a commutative ring with identity. All those verifications, the graduation students, you can try later. I will just only go through some of the examples and concepts and some important ideas. So another example, you might have studied this concept, that is integer modulo n. So integer modulo n means what? How it is coming? Uh, if you take any two real numbers, you can define a relation A is related to B if and only if what? N divides A minus B. That means A is congruent to what? B mod n. Then you can easily verify that this is an equivalence relation. From this, you can find out what the equivalence classes, and the possible equivalence classes, you will get it as what? Equivalence class containing 0, equivalence class containing 1, etc. Equivalence class containing n minus 1. So the same one, I am here denoting it by 0, 1, etc. n minus 1. So you might have seen that how to define the addition of two elements in this integer modulo n and multiplication modulo n. With respect to these two operations, you can see that this set n satisfies all the conditions of a ring. So it is another example for what? A ring. And for the first example, you know that set contains infinitely many numbers. So it is an example for an infinite ring. And here set contains finite number of elements. You can tell that this is an example for a finite ring. So next for you, these are the familiar examples. That is set of all rational numbers, set of all real numbers, set of all complex numbers. For the set of all rational numbers and real numbers, we can take the two operations, addition and multiplication, as the usual real numbers addition and multiplication. And for C, you have to take the addition of complex numbers and multiplication of complex numbers. So you can see that this is a example for a ring. And you come to this example. This is a slightly interesting example. You take X as a non-empty set. You take all the real valued functions from X to R, collection of all real valued functions from X to R. So till now we have seen that in the collections, the elements are numbers. Here the elements are what? Functions. So how to define the addition and multiplication? So addition of two functions. So if f is mapping from X to R, you take a G from this collection, then f plus G also will be a mapping from where X to R. For that one, how I am defining f plus G? F plus G of X, any element in the domain, is as f of X plus G of X. So this way of defining the addition is called the pointwise addition. Pointwise addition. And I am defining f into G of X, which is equal to what? F of X into G of X. This is what called the pointwise multiplication. So I am defining the pointwise addition as well as pointwise multiplication. You can verify that all the conditions for a ring will be satisfying for this collection under the operations addition and multiplication, so that this will be a ring. So my next question to students is, can you make this collection by modifying the operation multiplication such that it will not be a ring? So the way is, I am taking X is equal to R, to take that non-empty set as R. Then the above collection I am still restricting to set of all real valued functions from R to R together with addition and composition. How this composition will be defined? You take any two elements f and g from collection FRR, then f composition g of x is equal to f of g of x for every x in R. So with respect to this operation and addition, I am keeping same pointwise addition. The second operation multiplication, I vary to what? The composition. You can see that it will not be a ring. If it is not a ring, then which condition is violating? The condition which violates is the distributivity property. So to tell that it is not a ring, it is enough to show what? One counter example. So to show a counter example, I am taking f of x equal to x square, and other two functions g of x and h of x are x. So both all the three are real valued functions. So I will calculate f composition g plus h at some point. It is satisfying the distributivity property is satisfying means it should satisfy for what? All the points in the domain. If it is not satisfying, it is enough to tell what? At some point. So f composition g plus h at 1, if you calculate it by definition f of g plus h of 1, g plus h of 1, we can write it by pointwise addition. So g of 1 plus h of 1, g of 1 is nothing but 1. So this will be f of 2, f of 2 will be h square. We got this as f composition g plus h at 1. Then what will happen for f composition g plus f composition h at the same point? By the definition of addition, a pointwise addition, what will come? F composition g of 1, f composition h of 1. If you apply the definition of composition, you will arrive at it is 2. You are getting this as 2, and here you got 4. So what we are getting? This is not equal to f composition g plus h at 1. At one point, if it is violating, so that what we can tell, this f composition g plus h is not equal to f composition g plus f composition h. Hence, the left distributivity property fails here. Because of the left distributivity fails, you can tell that this is not a ring. So once we have a main structure ring, then we can think about what are the substructures. So I am taking a non-empty subset of a ring R. I am taking a ring R, and S is a non-empty subset of a ring R. This S becomes again a ring. This S becomes again a ring with respect to the same operations defined on what? The underlying ring R. Then you can tell that this non-empty set S is a subring. A subring means it is a non-empty subset which should be what? Again a ring with respect to the both the binary operations defined on R. So once we see the substructures, we are little much interested to see some of the examples of that one. So before going to the example, there is a necessary and sufficient condition to verify a non-empty subset to be a subring. Because here we have to verify means we have to verify all the conditions of a ring. So based on this necessary and sufficient condition, our full conditions are coming down to very less number of conditions. That is, phi is S is a non-empty subset of R if and only if what? S plus is a group, and the multiplicative identity belongs to S, and for any two element A and B in S, if AB belongs to S, then with these three conditions we can tell what the non-empty set S is a subring of R. That means if S is a subring, then these conditions will satisfy, and if these conditions are satisfying, then S is a subring. So these are our simple examples for subring. You know that C is a ring, and it is clear that Z is contained in C, and Q is contained in C, R is contained in C. That means all these three are non-empty subsets of C. All these are non-empty subsets of C, and they will be what? They will satisfy all the conditions of a ring with respect to the operations defined in where? Defined in C. So what we can tell, they are the subrings of the ring C. So next, you know that the singleton set 0, it is a subset of any ring, and R itself is a subset of R. So the set 0 and the two rings, the special rings set 0 and R, they are called the trivial subrings of a ring R. So once again, I am telling this concept will be very simple for teachers as well as MSc students and research scholars. My concentration is on graduate students. For them, some students maybe just started studying this one, some of them not yet started. So then for them, it is a new concept. So if you take this new set, you take a ring R. From that ring R, I am constructing a new set. That set is denoted by Z of R. What is the construction of that set of R? Those elements in this ring R, which are commuting with what? Every element of R. So those elements in R such that AX equal to XA. Those elements in R which commutes with every element of the ring R. So such subset will be again a ring of on what? The ring again a ring on the underlying ring R. So such rings are called the center of the ring R. So now I am going to some special type of rings. So for to define that special type of rings, you take a ring R. Right now you have a ring in your hand. So I am taking a notation here, R of square bracket x. The R of square bracket x denotes you take all the polynomials in x of degree n. All the polynomials in x of degree n. Then obviously the question will come, what should be the coefficient? Coefficient should be from the underlying ring R. You take a ring R and take all the polynomials, set of all polynomials in x of degree n whose coefficients from R. Then so now we have a collection R of x. So the next question is how to define two operation in R of x. So we can easily define the two notations. Before that, we can rewrite R of x. R of x is nothing but what I told you, that polynomials in x of degree n, that is a naught plus a1x plus a2x square plus etc plus an x power n, where each of the coefficient ai is from the underlying ring R. And you know, if you have a same degree two polynomials, how to add it? How we will add? We will add the corresponding same power degree terms coefficients, right? You will add up. So with respect to that usual polynomial addition and multiplication, you can see that this R of x satisfies all the properties of a ring. So such a ring, we are calling it with a special name that is called the polynomial ring in X, whose coefficients are coming from where? From the underlying ring R. So once we have this polynomial ring, so obviously the question coming in mind is, what will be their substructures? So one of the substructures of this one is, here you know that all the polynomials of in X of degree n, you just avoid the constant term. Then definitely all such polynomials, that is you avoid a constant term means you take a constant term as 0. So then all such polynomials, that collection will be a subset of what? R of x. That subset I am taking it as A. A is set of all P of x such that P of x is a polynomial in R of x with the constant term 0. Then with respect to the same operations what we defined here, addition and multiplication, you can observe that this R of square bracket x is a ring, and sorry, not R of x is a ring, A is a ring, and A is already a subset of R of x, so it will be obviously what? A subring of R of x. So another subring we can construct in this R of x is, you take the collection of all polynomials in x square whose coefficients are from where? R. You take the polynomials, set of all polynomials in x square whose coefficients are from R, then all such that's a collection will be obviously a subset of R of x, and you can verify what? All the properties of a ring for this substructure. So it will be a ring and it's a subset of R of x, so that it is a subring of what? R of x. Now we will see another class of ring. For that one, I'm going to talk about a unknown terminology here. Let X be a topological space. What do you mean by topological space? You take X as a non-empty set, and you take collection of all subsets of X. You take all the subsets of what? X in tau. If this tau satisfies some conditions, first one is phi and X should be in tau. Both of them should be in tau. And the second one is arbitrary union, arbitrary union of, sorry, finite union of, finite union of elements in tau should be in tau. And arbitrary intersection of what? Arbitrary intersection of elements in tau should be in tau. If these three conditions are satisfying for this collection of all subsets, then we call that what? This tau is a topology on X. And if you have a non-empty set together with a topology defined on it, it is called a topological space. You just understand this concept this much. You will study graduation. I'm telling to graduation students, you will study this concept much more in your topology subject. So I am taking what? One such topological space here, X, and R is nothing but what? The set of all real valued mapping from X to R. Set of all real valued mappings from X to R. So obviously the elements in R are functions. So again, here I will take the pointwise addition and pointwise multiplication. With respect to those two mappings, you can see that this C of XR, it is a ring, not only a ring, it is a commutative ring. Why it is commutative? Because the multiplication is defined as what? F into G of X is equal to F of X into G of X. And F of X is in where? R. G of X is in R. Multiplication is commutative in R. So you can write what? G of X into F of X, that is G into F of X for every X belongs to X. So that we can tell it is not only a ring, it is a commutative ring and with unity. Commutative ring with unity. So such rings are called a ring of continuous functions on X. A ring of continuous functions on a topological space. So I'm just illustrating here how the addition is defined, how the multiplication is defined, pointwise addition and pointwise multiplication, and what will be the additive identity here. Additive identity will be what? The zero mapping. We will denote it by zero suffix R, and the unity element will be what? We used to denote by one suffix R. So one suffix R is mapping from where? X to R, such that E corresponding to each X, it is mapped to what? 1. And additive identity will be what? Additive inverse will be what? Minus F. So with respect to all this, you can see that it is a commutative ring. Commutative ring with identity. So this class is the ring of continuous functions. So next, another class of rings that is named as matrix rings. So since it is named as matrix rings, then it is obvious that the elements in that rings are matrices. So to define that matrix ring, first I need to take a ring, capital R, and I am taking n greater than or equal to be an integer. Then I take a collection S. S is denoted by what? Denoted by Mn of R. What is the meaning of Mn of R? You take all n by n matrices with elements from ring. Each entries are elements from where? This underlying ring R. So you know, if the members in the collection are matrices, how to define the addition? That is matrix addition. You have matrix addition and matrix multiplication. So with respect to these two operations, you can verify the conditions of what a ring here. So such type of rings are called what matrix rings, and we know that matrix multiplication is not commutative. Since it is not commutative, what we can tell, this is a non-commutative ring. So this is also a matrix ring is an example for what a non-commutative ring. So next come to the very important concept in ring theory. What is ring homomorphism? So basically what homomorphism does. A homomorphism means between rings a homomorphism means it is helping us to compare the structural similarities. So if you are taking two rings, the homomorphism between two rings means you are one way what comparing the structural similarities. So next question is how to define a homomorphism between two rings. You take two rings R and R dash. Here R together with one addition defined on it and multiplication defined on it. R dash with another operation addition and multiplication defined there. So normally a homomorphism between two rings means it is a mapping, say phi from R plus to R dash plus, such that this mapping should preserve the operations. What do you mean by this map should preserve the operations? You take any two elements in the domain. So what are the operations here? Addition and multiplication. This phi should preserve addition means what? Phi of x plus y should be equal to phi of x plus phi of y. Where is this plus? This plus is from this ring. Because the moment phi of x comes, phi of x is an element in R dash and phi of y is an element in R dash. So this addition means it is the addition in the second ring. And it should preserve multiplication means what? Phi of x into y. This multiplication is in the multiplication defined on R should be equal to phi of x into phi of y. If these two conditions are satisfying for the map phi, then we will call that this phi is a homomorphism between the rings R and R dash. So that is what I defined here to take R and R dash. So it should preserve the operations. So the if you have a homomorphism between two rings, we can classify the homomorphisms into different categories. If the homomorphism is 1-1, if the homomorphism is 1-1, we call such homomorphisms as monomorphisms. If the homomorphism is onto, we will call such homomorphisms as epimorphism. And next one is very familiar to us. If it is both 1-1 and onto, we will call it as isomorphism. And for a homomorphism, if the two rings are same, such homomorphisms are called endomorphisms. That means endomorphism means what? If it is a homomorphism where both the rings are same. And in a isomorphism, if both the rings are same, then we call it as a automorphism. We call such rings as what? Automorphism. A automorphism is an isomorphism from same ring to itself. So once we have a homomorphism, we can get a nice structure from there. That is, you take the elements from the domain R, all elements domain from the R, such that phi is mapping to the zero element in R, the second ring R dash. So such collections are called the kernel of a homomorphism. The kernel of a homomorphism is nothing but what? Those elements in the ring such that the image of that element will be the zero element in R dash. And similarly, you can define image of that mapping. Image of that mapping is nothing but set of all phi of a such that A belongs to R. So once we have this kernel of a homomorphism, we can immediately see a property for kernel. So kernel of any homomorphism will be a subring of the, sorry, this is not real numbers, this is the underlying ring R. It's a typo. So kernel phi is a subring of what? R. And next you can see, if you take the multiplicative identity in R, then phi of IR will be what? If phi is a homomorphism, phi of IR will be what? The identity element in the image collection. For IR is the multiplicative identity in R, means if phi is a homomorphism, phi R will be what? The identity element in the image collection. So next one, I told you that kernel of any homomorphism will be a subring of R. Similarly, you can see that image of a homomorphism is also a subring of what? The second ring R dash. So next, one obvious question will come in our mind is, if you have a subring of a ring, whether the identity of a subring is same as identity of a ring. It is not in general true. If it is not in general true, means we can show it through an example. You consider the integer modulo 6. If you take the integer modulo 6, you know that the identity element is the class containing 1. So from this integer modulo 6, you can take a subring, that is integer modulo 0, class 0 and class 3. So this is a subring of Z6. But for this subring, the identity element is 3. So that means here the identity element of underlying ring is 1, and the identity element of this particular subring is what? 3. So this clearly indicates that the identity of a subring need not be identity of ring. So that is what I mentioned here. So next, I will move on to one of the important concept in ring theory, one important structure, that is ideals. So before telling the formal definition of ideals, we can just correlate this ideal concept with some concept we have discussed in group theory. So in group theory, you have studied about normal subgroups. In group theory, you are studying about normal subgroups. So if normal subgroups are there for groups, means for rings, the analogous idea in rings is nothing but ideals. So we can tell a similarity between that one. That is, if normal subgroups are there for groups, then ideals are for rings. Whatever the most of the things we are discussing for normal subgroups in groups, we can take the analogous for what? Ideals in rings also. So the moment you are talking about the normal subgroups in groups, you will discuss about what? The idea of cosets, factor groups, kernel of a homomorphism of groups, etc. Similarly, you can think about what? The factor rings and quotient rings, factor rings or quotient rings, and all other similar analogous results here. So now we will go to the formal definition of ideals. So to define an ideal, I am taking a subgroup S of the abelian group R plus. You know that if R is a ring, then R plus is a abelian group. From that abelian group, I am taking a subgroup. So this ideal concept can be of 3 types based on some condition. This S is said to be a left ideal if you take any element from the underlying ring R and any element from the subgroup. If R into A belongs to S, that is left multiplication we are doing, R into A belongs to S, then we can tell it is a left ideal. So obviously, if R into A belongs to S, means if what will happen if A into R belongs to S? If A into R belongs to S means such subgroups are called right ideals. If both the left and right multiplication belongs to S, then we will call it as two-sided ideal or ideal of a ring R. If both the left and right ideal conditions are satisfying for what this subgroup is, then we will call it as a ideal or two-sided ideal of the underlying ring R. So if you take any subset which is a left or right or two-sided ideal, then immediately you can see that that ideal is a subring of R. A subset S is a left or right or two-sided ideal in the underlying ring R. You can observe what it is a subring of R. But the converse is not true. Why the converse is not true? You take this example. You take the ring of rational numbers. You know that for the ring of rational numbers, the only ideals are set 0 as well as q. The only ideals of rational numbers are what? Set 0 as well as q. And you know that z is a subring of q, but it is not an ideal of what? Q. Z is a subring of q, but it is not an ideal. So this example will illustrate that what? The converse of the above remark is not true. So you take any fixed n, an integer n, you can see that n into z, you know that n into z is what? Set of all n into x such that x belongs to z. N into z is an ideal of what? Z. For any fixed n, n into z is an ideal of z. So you take this, we have discussed about the ring of polynomials R of x. So ring of polynomials R of x, we have discussed about two types of rings. One is the ring what? Ring of polynomials in R of x with constant term 0 as well as R of square bracket x square. So these two are, we have told that they are the subrings of what? R of x. So obviously you can verify that they are the ideals in R of x. You can verify the left and right ideal condition here. So you can see that in ring of polynomials R of x, what the subrings set of all polynomials with the constant term 0 as well as R of x square are what? Ideals in R of x. So next is, if you have a commutative ring, if you have a commutative ring, in that case, this left ideal concept and right ideal concept and two-sided ideal will coincide because the commutativity property is there. So left ideal, right ideal as well as two-sided ideal concept will coincide. We will separately see the left ideal, right ideal, two-sided ideal concept if the underlying ring is not commutative. So if you see any ring, you can see that that ring is an ideal in itself. Every ring is an ideal in itself. So such rings are called unit ideals. So unit ideal means what? Every ring is an ideal in itself. So such rings are unit ideals. And you know that the set 0 is an ideal in R. Then such ideals are called what? The 0 ideal. I'm just telling what are the different types of ideals. And just now I told you that the unit ideal as well as 0 ideal. The unit ideal and 0 ideal of a ring are called the trivial ideals of that ring. For any ring, you can tell that the 0 ideal and the unit ideal are the trivial ideals. So next, I am taking the set of all 2 by 2 matrices whose elements are coming from a ring R. I am taking set of all 2 by 2 matrices M2 of R whose elements are from the ring R. Then if you take a substructure of M2 of R, that is set of all 2 by 2 matrices with what second column is completely 0. And another subcollection I took what set of all 2 by 2 matrices with the second row is completely 0. So such collections are, this first one is a right ideal and the second one is a left ideal of what M2 of R. So next comes to the other example we have discussed. We have discussed that this f of xr, the f of xr is what set of all functions from where x to r, set of all real valued functions from x to r. From this one, you take a subset S of x. You take a subset of that underlying non-empty set x. Then you construct a set of this form I suffix s is equal to set of all mappings from the underlying collection such that f of s is equal to 0. Those elements from s which are mapped to 0, such functions you take as elements in this is, then you can easily verify that they are the ideals of what f of x are. So next, to define the to tell the next concept, I am considering a ideal in a ring R. I am going to define a relation on I. That relation is denoted by tilde. How I am going to define that relation is, take two elements A and B from I. A is related to B if and only if what A minus B belongs to I. So you can easily verify that this is an equivalence relation. You can verify that it is reflexive, symmetric, and transitive. So once you have an equivalence relation, you can get what the equivalence classes. You can find out what the equivalence classes of that. So the collection of such equivalence classes. So this equivalence relation will give what equivalence classes. So you take the collection of all such equivalence classes, that we are denoting it by what? R over I. We are writing it by R over I. So how we will write the elements in R over I? Elements in R over I is nothing but what? We will write it as A plus I. So how to define, if you know the elements in R over I, how to define addition and multiplication there? You take two elements in R over I. Elements in R over I is of the form what? A plus I, where A belongs to R. You take A plus I and B plus I are two elements in R over I. You can define the addition by what? A plus I plus B plus I as A plus B plus I. And A plus I into B plus I you can define as AB plus I. So with respect to these two operations, you can see that this set R by I satisfies all the conditions of a ring. So that means now we are using an equivalence relation on the ideal of a ring R. We constructed a new class, new set collection R by I, on which we defined addition and multiplication. And now we gave a structure to it that becomes a ring. So such rings are called the quotient rings. And this R by I is not only a ring, it is a commutative ring also, and it has identity element. And such rings are called what? The quotient rings. So once we have a quotient ring, so we can easily construct a natural homomorphism between the ring and the quotient ring. So for that one, you take a ring R and I be an ideal of R. Then we can find out what a natural mapping from R to R by I, how it is going. You take a element in R, it is going to that corresponding A plus I. Then you can see that that mapping is Not only a homomorphism, it is an onto homomorphism. And with what additional information? If you calculate the kernel of that homomorphism, it will be nothing but the ideal. So what you are getting from this one, you are getting that there is a natural homomorphism between the ring and the quotient ring, such that it is onto, as well as the kernel of that homomorphism is nothing but what? The corresponding ideal. So now we can generalize this idea of ideals and kernels to any ring homomorphism. So how it is? If phi is a homomorphism, ring homomorphism between R and R dash, then you know that kernel of phi will be an ideal of R. If phi is an homomorphism from R to R dash, then what we can tell? Kernel of phi is an ideal of R. This will help you to identify the ideals on a particular ring R. So you know that if R and R dash are same, then such homomorphisms are called what? Endomorphisms, right? Endomorphisms. So this result will hold for that case also. That means what? If you are able to find out an endomorphism between what? A same ring, then obviously their kernels will be an ideal of what? That ring are. This result will give you one technique to find out what? The kernels of any ring. To identify the kernels of any ring, to identify what? The endomorphisms between the given rings, and then calculate the kernel of that endomorphism. So that will be the ideal of R. So after all this, we have one very famous theorem. That theorem says that what? If you have a ring homomorphism between the ring and the quotient ring, if you have a ring homomorphism between the ring and the quotient ring, then the image of that homomorphism will be isomorphic to R by kernel phi. Image of that homomorphism will be isomorphic to R by kernel phi. So that result is famously known as first isomorphism theorem. So if you have a ring, you take an ideal from that ring and with identity 1, then if I equal to R, if and only if what we can tell, I contains a unit. If you have an ideal in a ring R with unity, with a identity element, then this ideal will coincide with what ring? When if I contains the unit. And if I equal to R, then what is obvious? I contains the unit element. So next, if you take a commutative ring R, if you take a commutative ring with identity 1, we can call it as a field if and only if it has only two ideals that are 0 and R. That is, if the commutative ring with identity has what? The trivial, only the trivial ideals, then such commutative rings with identity is called what? Is a field. This is a necessary and sufficient condition. So next, these results you have studied. If you have any homomorphism between two rings with the kernel is known, then what we can tell? The homomorphism is 1, 1 if and only if the kernel is set 0. So these proofs are very interesting. I am not doing it here. So next question I wanted to ask is, what are the ideals in the quotient ring R by I? What will be the ideals in quotient ring R by I? So the ideals in R by I means, the ideals in R by I are what? In one, it is a they are with one correspondence with the ideals of R containing I. If you want to find out the ideals of R by I, they are nothing but what? They should have a one correspondence with the ideals of R containing the ideal I. So that correspondence will give you what the ideals of the quotient ring R by I. So that means what? The ideal in R by I is of the form some J by I, where J is an ideal of R containing I. Right. So the next question is, if you have a ring homomorphism from R to R dash and I is an ideal of R, can you tell that phi of I is an ideal in R dash? That is a question. Can you tell that phi of I is an ideal in R dash? The answer is no. Why? You take this counter example. Phi is a mapping from Z to Q defined by what? Phi of nz equal to nz. Then you can easily verify that phi is a ring homomorphism. And you know that nz is an ideal of Z. But phi of nz equal to what? Nz, which is not an ideal in Q, because in ideal in Q are only what? 0 and Q. 0 and Q are the only ideals in what? Q. Whereas phi of nz is coming out to be what? Nz. So what we can tell? This counterexample will give you that if phi from R to R dash is a ring homomorphism and I is an ideal of R, then phi of I is not an ideal in R dash. It is not generally true. So the next question is, if you have a ring homomorphism phi from R to R dash and J is an ideal of R dash, can you tell that phi inverse J is an ideal of in R? So the answer is yes. It's a very simple verification. I am leaving that verification to students. You can verify that one. If you have a ring homomorphism between R to R dash and J is an ideal of what? R dash, then phi inverse J is an ideal of R. So next we have to just go through some of the concepts. You take a ring R, then these are the non terminologies for you. What do you mean by unit? Unit means what? An element in a ring is said to be unit means if it is invertible. That is, if there exists what? V belongs to R, such that U into V should be equal to V into U should be equal to the multiplicative identity. First of all, R is a ring with identity. Any element in R is said to be a unit means what? If you are able to find out V such that U into V equal to V into U equal to 1. What do you mean by zero divisors of a ring? You take an element in R, it is zero divisors are of two types, left zero divisors and right zero divisors. So A belongs to R is to be a left zero divisor if you are able to find out a non-zero element B such that A into B equal to 0. If you are able to find out a non-zero element B such that A into B is equal to 0, then such elements are called what? Such A element A is called the left zero divisor. And if we are able to find out a C such that C into A equal to 0, then that element A is said to be what? A right zero divisor. If both left and right holds means it is called a zero divisor. If you are able to find out a non-zero element such that this left product and right product is equal to 0, then you can tell what it is a zero divisor. So if you take a ring with at least two elements, then you can see that the element 0 is a zero divisor, and this zero divisor is called the trivial zero divisor. In a ring, if you have at least two elements, then the zero element is a zero divisor, then such devices are called what? Zero devices. Then what do you mean by a nilpotent in a ring? A nilpotent in a ring means it's an element in R such that if you are able to find out an n which is greater than or equal to 1 such that x power n is equal to 0, then we can tell what such elements are called the nilpotent elements. So for any ring, we know that 0 is a zero divisor that I told just now. If you take the ring of integer modulo 6, you can see that the class containing 2 and class containing 3 are zero divisors of Z6. And if you take the ring of integer modulo 4, there you can see that the class containing 2 is a nilpotent element, because if you take the class containing 2 square, that means you are multiplying twice. So it will be what? The class containing 0. So you can tell that this is a nilpotent element in set 4. So any non-zero element in a field is a unit. So you can see that, you know, that the idea of field, in a field you can tell that what every non-zero element in a field is an unit. So you can see that a nilpotent in a ring is always a zero divisor. A nilpotent in a ring is always a zero divisor. But the converse is not true. Every zero divisor is not a nilpotent element. You see this example. If you take the ring of integer modulo Z6, the element class containing 3 is a zero divisor, we know. But it is not a nilpotent element. If you cannot find out an, there doesn't exist what? An n such that what? The class containing 3 power n equal to the class containing 0. So if you take any ring R, if you, and you take the collection of all zero divisors and the collection of all units, you can see that they will be always disjoint sets. If you take the collection of all zero divisors of a ring and the collection of all units of a ring, they are disjoint sets. So actually I wanted to tell something more. I think 1 hour exceeded, I think, as per your schedule. Can I continue for 10 minutes?
Okay, sir. Okay. Okay,
Okay.
Hari.
Okay. Okay. You next we can see what do you mean by a division ring. You take a ring R in which I am taking a set R star. R star is the set of all non-zero elements in a group. So you take a ring R in which a set R star of non-zero elements, if it is a group with respect to multiplication, then such collections are called what? Division rings, or we call it as Q field. From a ring R, you take a set R star. R star is the set of all non-zero elements, and if it forms a group with respect to the multiplication, then such sets are such rings are called what? Division rings. And in other way, we are, how can we tell that R is a division ring if every non-zero element of R has a multiplicative inverse? Because here you know that in a ring R, R dot is a semi-group, right? R dot is a semi-group. We are telling that take the collection of all non-zero elements of that R as R star. If it is a group with respect to multiplication, then we are calling it as a division ring. That means R is a division ring if every non-zero element of R has a multiplicative inverse. So the very simple examples for division rings are what? Q, set of all rational numbers, real numbers, as well as complex numbers. They are division rings. So this is a very interesting topic in algebra. So majority of the students, the degree students, will study only if you go to the PG classes. So what do you mean by integral domain? I will tell some more ideas and I will wind up. What do you mean by integral domain? For to define an integral domain, you take a commutative ring with identity. You take a commutative ring R with identity. If the only zero divisors of R are 0 and 0, then what we can tell, if the only zero divisor of R is 0, then we can tell R is a integral domain. In a commutative ring with unity, if the only zero divisor is 0, then we can tell what it is a integral domain. So the simple examples are set of all integers, set of all rational numbers, set of all real numbers, set of all complex numbers. They are integral domains. So here you can see an example here. Consider a ring f of xr. This is an example we have seen there. You take a set x, x is equal to set AB. Define two mappings f and g from x to r. You remember that this x is two element set. I am taking f of a equal to 1 and f of b equal to 0, and g of a equal to 0 and g of b equal to 1. Then you can see that fg equal to 0 in x, but neither f nor g is 0. So I am telling here in the definition of field in a different way. You might have studied in linear algebra the definition of field by satisfying 9 conditions. Here we can tell a field means a commutative division ring is called a field. You know that what do you mean by division ring? So if you add one more condition to that division ring, then such division rings are called what? A field. So the examples you have studied in fields are Q, R, and C. So you can see that every field is a division ring and every division ring is an integral domain, but not conversely. You can see that every field is a division ring and every division ring is an integral domain, but conversely, it is not true. Example for an integral domain which is not a field. Integral domain which is not a field is, you take this ring of integers. If you take the ring of integers, it is an example for an integral domain, but it is not a field. So the example for a division ring, but it is not a field. What will be? So this example will make sure you that the converse of the above result is not true. So you take the set of all 2 by 2 matrices of this form. Then this collection is a ring with respect to matrix addition and matrix multiplication. And you can see that every non-zero element in R has a multiplicative inverse in R, so that it will be a division ring. As matrix multiplication is not commutative, you can see that what it is not a field. So this example will give you what this example and the previous example will give you that the converse of the previous result is not true. So I have told about what do you mean by R of x. R of x is nothing but what? The ring of polynomials. So if R is the underlying ring is an integral domain, then the ring of polynomials will be an integral domain. In the polynomial ring, if the underlying ring is an integral domain, then what we have? Then R of x is an integral domain. So I thought to prove that one. I am skipping that proof. You can see later. So this is a next result is a very good characterization of field. That is, if you have a commutative ring with identity, then the following results are equivalent. First one, R is a field. R is a field implies the only ideals of R are 0 and R. Then which will imply what? Any non-zero homomorphism from R to a non-zero ring R dash is injective. So this is a very good characterization of what? Characterization of ring. That is a commutative ring with ring identity is there, means these three results are what? Equivalent. So with this one, I would like to wind up because I have some more content, but it will take too much time. And the very good books you can refer for this rings and ideals is you can refer the book. I will show you 1 minute. One good book is Introduction to Rings and Modules by Musli, and Rings and Modules by Nadia and Krchenko. So these books will give you a clear idea about the fundamentals of rings, ideals, and modules. So if you have any queries, you can contact me to these IDs. So with this one, I would like to stop my presentation. Once again, I would like to thank Professor Rauf and team for giving me an opportunity to talk to you.